Shall we start?
Yeah.
So, it's a great pleasure to have Professor Ramadevi today as speaker, who agreed to come despite a very busy schedule. So, Professor Ramadevi is a mathematical physicist and a professor in the Department of Physics at IIT Mumbai. Her research focuses on Chern-Simons field theory, knot-invariants, string theory, supersymmetric quiver theories, and ADS-CFT correspondence. Professor Pichai received her PhD from the Institute of Mathematical Sciences, Chennai. She is a recipient of IIT Bombay Research Publication Award in 2016, IIT Bombay Research Paper Award in 2006, Junior Research Associateship Award ICTP from 2003 to 2007, Senior Research Associateship Award ICTP from 2019 to 2024, Professor S.P. Shukhathme Excellence in Teaching Award 2023 and Departmental Award for Excellence in Teaching 2023. So let's welcome her. Today she's going to talk about Chern-Simons field theory invariants. Thank you.
Thank you, Rukmini. Thanks for this invitation. It feels nice to be in ICTS. I think I came 5 years ago. I feel really good when I come here. I would like to come for a longer time. I hope I find longer time to come, maybe next time. So this is something which a lot of work has been happening in the last so many decades. So I thought there'll be new influx of students who are not very familiar. So it's a colloquium talk. I'm going to pitch it little, really, trying to give some kind of a motivation. And towards the end, I'll tell you what all we have been doing in the recent years. That's the plan. So just as a take home, even if you haven't registered a lot of things, at least these figures should get into you. Trefoil and figure 8 are some things which are very important, and not Atlas has these figures. I didn't draw these diagrams. And so basically I work in quantum field theory, and these aspects of topological features, we can get insight from topological field theory. So that's the reason I chose Chern-Simons field theory invariance as the title. Okay, so why, as I already said, there are a lot of challenging questions in the interface of mathematics and physics, especially in the low dimensional manifolds. 3 and 4 are a lot of challenging problems, are there? And one of the important challenging question is, like, I remember some of these, this Brian Greene string theory, elegant universe, it will keep beeping, unification, unification, unification. Similarly here, the main theme is classification, that's still an open question. And of course, the physics approach has been really very, very elegant, and a lot of things which requires detailed pages and pages of calculation to be done at the mathematics front can be elegantly handled from physics approach. So that is why I find this very fascinating. And especially it started off in 1988 with Witten. So I would say like 35 years. A lot of interesting developments have been happening in this interface. So I thought I will share with you. Okay. Okay, so this is something which even in the middle of the sleep, if anybody calls you and asks you what is calcium, what is bromine, chlorine, you know what the letter means, and you also know roughly, each one has different atomic weight and atomic number, so that combination classifies all the elements. Okay, so this is what you call it as a classification, where no two elements will share these two quantities together, right? That's what you know. Isotopes will have some change, so that's the way it is. But why am I bringing this periodic table? Historically, in 1857, Kelvin came up with this thing that he said, I don't like this rigid point atom. He wanted to bring in a fluid mechanical model, so where atoms are like vortex lines knotted in the ether medium. So this is what was his prescription of this fluid mechanical model of atoms. So then the next question is that they like this idea of vortex lines. And then there is a periodic table, which we saw should be seen as periodic table of knotted things. And it's very beautiful. It can be, it's like just like the way you saw the periodic table, you can see the periodic table where they are, all these atoms can be seen like vortex line knotted in another medium. And each one has, the 3 refers to 3 crossings, 4 refers to 4 crossings, 5 refers, in fact in 5 there are 2 distinct topologically inequivalent objects, okay, 2 inequivalent objects. So you see that the crossing number is not very good. Okay, just like atomic number and atomic weight, you don't see the crossing number to be a very good thread to distinguish the atoms which are knotted vortex line in either medium. Okay, so this is what sometimes they call it as a periodic table of knots. Interestingly, so the next other thing is that's just a single vortex line, but you can have 2 different colors to denote 2 different types of vortex line entangled. A lot of works going on in the entanglement structures and how to see, entanglement informations and so on, but let me not get into that. But here I'm just looking at it as a couple of curves which are entangled. Hoff-Link is the name given to 2 such curves, and there are 3 colors. Maybe these 2 colors are not looking very different, but there are 3 such curves which are put in, and this is known in the knot theory as Borromean links. Sometimes I think math science has this logo of Borromean ring, and formally you can draw it as a curve projected onto this 2-dimensional screen with overcrossings and undercrossings to take care of the diagrams. That's the usual convention which we follow, but they are non-trivial only in 3 dimensions. Okay, so this is something which is very important, that all these curves which we draw is non-trivial only in 3 dimensions. If I go to 4th dimension, you can still undo things and make it into a simple loop. Okay, so 3-dimensional physics is what is being captured by the knots or links. Okay. Yeah, this is also something which I found interesting. Efimov states, I don't know how many of you have seen, it's still controversial that theoretically it was just like you have 2 body interactions, there can be 3 body interaction which could collectively give you a nested doll structure, which they call it as an Efimov states. And sometime recently they have tried to synthesize experimentally, they call it as a surprising rule of 3s. Anybody is interested can look at this Quantum magazine to read about this. Okay, so they're trying to synthesize such kinds of strange state of matters formed by 3 particles together. Okay. Okay, so coming back to my periodic table, either is of course a question mark, it's been ruled out. So then all the physicists lost interest in knot theory. Of course, mathematicians got into it and they worked on this field of knot theory. Until 1988, it's when, physicists again got back using topological quantum field theories. Okay, so that way it is, the history is something which is very nice. Then this book is also very interesting. Why Knots? An Introduction to Mathematical Theory of Knots by Colin Adams. This book talks about various interfaces, branches in maths and physics, interestingly interact via knot theory. So I suggest you take a look at some parts of these books. To put my kind of interest, the central theme was knot theory. I got very fascinated by this. But then a lot of other things, of course, mathematics was the main driving area in which mathematics to knot theory was there. And I wanted to get a lot of interesting things out of this. And I also saw that some of the enzymes at the synaptic nodes can lead to knotting structures. I was very much interested in looking at whether a cancerous cell could become non-cancerous. Can we model it? And there were some models for topoisomerase enzymes. So I found this area also interesting. So far, I have not really made progress. One of the reasons is probably the wavelength between biologists and physicists is not still happening. Because this was also, they tried to make stereoisomers, knotted molecules, structures in chemistry. And computer science, where they look at complexity issues, they wanted to look at the unknotting structures. The Borromean ring, if you remember, if I cut one of the curves in the Borromean ring, the other two falls apart separately. They don't get entangled. So those are called the unknotting numbers, and there are ways in which you could study NP-hard, or also the three satisfiability problem is NP-complete, NP-hard issues could be studied by mapping those unknotting structures of these, not only three components, multi-component generalization. So this, I was involved during my student days with Manindra Agarwal, and a lot of interesting things I learned. So that way I find that this area is very interdisciplinary, but even within our physics, there are a lot of connections. The vertex models, where you study Yang-Baxter equations, exactly solvable models by integrability criteria. They have ways of connecting the braid group representation as the connecting link which connects to knot theory. And quantum groups, the universal R matrix in the deformed conventional groups, which we all know when you do the quantum groups, the universal R matrix have connections to the braiding matrices. Of course, Chern-Simons is the path which I have taken for nearly 10 years in understanding the classification issues. Okay, so this is just to give you a broad flow chart of how things are all interlinked. The other thing which I have been very also excited, since I was also looking at string theory, learning string theory, and Chern-Simons theory is a three-dimensional. So this thing, you can take it to be some kind of a three-sphere, and knots are inside the three-sphere. As I said, knots have non-trivial meaning only in three-dimension. The whole thing is sitting in a target space, unlike your string theory where you want your target space. The conventional ones have either 9+1 for supersymmetry or 25+1. This is a six-dimensional Calabi-Yau space, Calabi-Yau threefold. And typical physical string theories, you look at effective terms in the 3+1 dimension, which you see it as a cross, a Calabi-Yau. Those effective terms can also be captured by studying these topological string theories. Okay, so I've just put it like a cartoon picture to show that we are interested in three dimension, but certain terms in three dimension in this low energy effective action can be captured by studying. And inside this is this connection, which also makes it like an ADS-CFT correspondence. And these works were done immediately after Malachena by Gopakumar Vafa at the partition function level, partition function of Chern-Simons theory. And then Oguri Vafa used this Gopakumar Vafa ADS-CFT quote-unquote correspondence to look at knot invariants also. It's very beautiful. And at the same time, the mathematician Kohanov also came up to look at how things are related. Okay. Well, one of the things which I find it very fascinating is that the knot invariants, they were like a Lorentz series with integer coefficients. And those integers can be accounted by counting the number of BPS states here. And Kohanov came up and said that he can account it as a dimension of some vector space. Okay. So in that sense, anytime you get an integer, there is always a question. Integer has meaning only if it is positive integers, it has meaning only if it is a number of solutions to an equation or a dimension of a vector space. So why it is an integer, people have been bothered from the early this century. Okay. Any questions you have? I'm just giving you a broader picture. I'll get in a little more into details. Okay. Okay, so as I said, this area is in the interface of mathematics and physics to start with, where knot theory was initially by mathematicians and then physicists took over. Why 3D? Why can't we do 2D? So 2D, you all know that 2D Riemann surfaces, two-dimensional surfaces are completely classified, right? Like genus, punctures, and Euler characteristics, triangulating the surface you can do, and you can completely classify them. That there are no two surfaces which have the same genus. That a donut is different from a sphere, and you don't find another surface which shares the same. So it's completely classified. So by triangulating the surface, you can, by vertices, edges, and faces, you can write a mathematical quantity which is your Euler characteristic, and you can completely distinguish every surfaces. And sometimes even in field theory, when we do gauge theory, instead of using those, in gauge theory, you can have matrix valued gauge fields, you can put a double line formalism and you get theory of surfaces. That's why TUF's thing where every gauge theory can be given a interpretation of a closed string, because these Riemann surfaces are like the world sheet interpretation. Okay, so a lot of connections. So that way 2D has been really very well understood. Okay, but what about 3D? In 3D, before even we go to manifolds, as I said, knots are non-trivial curves in 3D, right? First thing is, as I said, the atomic number, atomic weight, can I find, crossing number is no good. We have already seen 5 crossing, 2 knots at the same crossing number. You need to classify, or you need to find a mathematical quantity. Yeah.
Sorry, so when you talk about knots in 2D, you mean knots which are on Riemann surfaces, is that right?
No knots here. Previous one is 2D. 2D surfaces are all classified.
Yeah, but
now I'm going into 3D surfaces.
Knots.
Even to do 3D surfaces, before that I want to even do knots in 3D.
Okay, but you were not talking about knots in 2D.
There is no knots in 2D. Knots in 2D will become, just you can't put an overcrossing or undercrossing. You have to intersect somewhere.
I see.
So there is no point in talking about.
Yeah, okay.
You need overcrossing means you have to go above.
Okay.
So knots become non-trivial only from 3D,
3D
onwards.
Sorry. Yes.
So similarly, instead of single thread, if you put a tube, then it becomes non-trivial in 4D also. So you can start putting knotted surfaces and so on in 4D. But right now, I'm just saying that I would like to classify 3 manifolds. Even before I classify 3 manifolds, the first interesting question is knots are non-trivial in 3D. Can I classify knots itself to start with? Okay. So there is no concept of knot in 2D. Okay, so what did I say here? Crossing number is non-trivial. You know that this has 3 crossings, whereas this has 4 crossings. I've just drawn it like a tube, but treat it like a single line in 3 dimensions. And this I've already emphasized, that crossing number, there is a 5 crossing knot, 2 different knots which share the same 5 crossings. So it is a very weak invariant. Okay. And if you go to links, then you start looking at linking numbers also. So at every crossing, you look at the sign, you put either plus sign or minus sign depending upon whether it's an overcrossing or undercrossing with orientation. And then you count those signs and take half of it, because whenever it crosses one component, it has to come back. Equal number will be there. So this will always give you an integer. And for example, I've drawn this as a half link. There is the other complicated links are drawn here. So you can count and see that there's linking numbers. Linking number is again going to be a very weak link invariant, because you see that linking 0 can also happen if you have 2 in unlinked objects also, right? So linking number is not a very good invariant. But I'm just pointing it out where things were. The Gauss linking number had an integral form, and these integral forms can be compactly written, but in Chern-Simons, you can show that this is related to the propagator in Chern-Simons theory. Okay, and the simple Biot-Savart's law, which we have all learned in electrodynamics, to move work done to move a monopole, let's say, over one loop due to an electric current in the other loop, those are captured by the linking number, and a mathematician will look at it as a map from 2 circles to S2. and look at the degree of that map to give the linking number. Okay, so it's very nicely the ways in which physicists see, the ways in which mathematicians look at this. So what did mathematicians do in between that era of 1900 to 1980s? I'll just quickly give you what is required. So there are, clearly by seeing this diagram, you know that you can undo this and make it look like a simple loop because you have this extra dimension in your hand, right? Three-dimensional space. These two are very clearly equivalent. But if you look at this and this, you need to do some more hard work to see whether they are equivalent or not equivalent. So this has been given by a prescribed set of rules, I would say. So those rules are what we call it as readmaster move 1, 2, and 3. In any region, if you have something like this, you can make it this way. If you have two of them going below the plane, you can slide it across, and you can even slide this down. So these are the three moves you are allowed to do on any region, even in the previous diagram. And if you can go from one to the other, then you will say they are equivalent. Is this clear? I hope I'm not very fast. Okay. So now I also said weak invariant crossing number is useless. So I need to find some other algebraic quantity which can tell me that I can distinguish two knots with same crossing number, but they are actually topologically inequivalent, right? So this is the Jones polynomial, which was put in. Actually, I should say Alexander came up much earlier in 1920s, and he put forth a polynomial. The only unfortunate thing is, for any disjoint pieces, it was 0, and also if you take a knot and take the mirror image of the knot, it gave you the same answer. So Jones came up with a much better picture where we could get a much more better invariant. So that's why I started with Jones, but Alexander is historically the earlier one, 1920s. Okay. So how does Jones find this polynomial? Is he takes this trefoil, for example, concentrates on one particular crossing. So if you see this crossing, I have changed this crossing to an undercrossing. That's the modification. So below is for any arbitrary diagram, you concentrate on one crossing. If it is an overcrossing, make it an undercrossing. And the other one is, since the arrows are there, you make it into a no crossing without changing the convention of the arrows. So this is a no crossing. So there is a nice recursion relation or a skein relation which relates whatever, this is trefoil anyway, what new knot you get by making it as an undercrossing. After you do that, you do readmaster move 1, 2, and 3, what knot you get from here. And similarly here. See, here you can clearly see it is a Hoff link. This one you can show finally, I think it's an unknot. Okay. So you can write a skein relation amongst these three. And that skein relation is what is going to give us a Jones polynomial. If you know the Jones polynomial for this lower crossing and this lower crossing, you can find the Jones polynomial for this. Okay, and we also use that unknot, a simple loop. In Jones knot theory literature, they took the simple loop, that J of that simple loop to be 1. Okay, so with that, J of that simple loop to be 1, and J of two simple loops together is taken to be this. They could determine, for example, we have done it here explicitly. You can verify later. The slides will also be there. So you will see that this will give you the, and I pointed it out that the polynomials have integer coefficients. And these integers was bothering the people in the topological strings as well as the mathematicians, why they are integers. Okay, so that is one thing which led to early century of this year. Lot of developments happened in this. Why it is integers. So not only for this example, any complicated example, things are integers. Now with AI, I think Vishnu Janjala was saying, I want to do some 300 crossing, 200 crossings and so on. So a lot of things can be now done because the methodology is there. Okay. Okay, so all these knots can be, as I said, when I did the exactly solvable models, R matrix, universal R matrix, the main connection is the braids. And these knots can be viewed as closure of braids, which I'll give you. This is Alexander's theorem, but I'll give you a pictorial view of what is a braid. So these are like, you can take it to be n particles on a plane, or you can take n strings, which is moving in time. That's another way of looking at it. Sometimes two particles can exchange between each other. That exchange also, since it's on a plane, if you do a clockwise exchange, it is different from an anti-clockwise exchange. If it is clockwise, we put it as overcrossing on this diagram. If it is anti-clockwise, you put it as an undercrossing. And then the group action is just concatenation. If you keep doing it clockwise followed by an anti-clockwise, it will give you back the identity element. But you can use this generators to make arbitrary words. So arbitrary words, for example, here I've done between 1 and 2 such overcrossings. I'm calling it as B1 squared. And between 2 and 3, it is 2 such crossings, B2 squared. After I've done it, I'm going to identify the initial time with the final time. That's what you will call it as a trace. I've shown it by a dotted line. Once I do the dotted line, which is what we call it as a closure, what you get eventually is a knot or a link. So closure of a braid is going to give us a knot or a link. Or equivalently, I would like to draw every knot as a closure of such braid words. Okay. And there are some interesting relations. It's not a free group. Any arbitrary word will not give you a distinct braid. If you do between these two crossings and any of these last two strands, you can interchange. It doesn't really matter because ultimately it is the same. But if it is consecutive, then you need to worry. If BI you do and then BI plus 1 and BI, this is nothing but, if you look at Yang-Baxter equation, which is dependent on some spectral parameter, in certain limit, it will become the braid root relation. Okay. So in that sense, this is also very important connections to statistical mechanical models. So, yeah. Correct.
Yeah, but this braid group structure that you talked about,
yes,
and how it maps into knots is in 3 dimensions, right?
Yeah. So the thing is, yeah. So when
So is there some sort of way of looking at the Yang-Baxter equation here in the 3rd dimension? Is that?
So as of now, we look at it as if, see, when we do things, we look at it as if it is like a 2D model, but the representation which we get is what we extract when we do the knot invariants. We look at it as a representations. Just like spin half particle is 2-dimensional vector space, I can still use the SU2 algebra to do the spin 1, which is 3-dimensional vector space, right? In some sense, I'm using the representation theory of braid groups, which is applicable in 2D, to study knot invariants in 3D. So there I'm only looking at the representations. Yeah. But since you're asking this, there is also some works where one of the direction is taken as complex coordinate, and Kevin Costello has done some interesting works which has many connections to integrability. So still I don't have too much of insight into it. I've been looking into it, but I've not really got into that. Yes. Yeah, so these are the formal things as he has already said, it's in a 2D model. And if you do a braid word B and then an A, or a B, A and a B, because of this identification, trace operation, it doesn't really matter. Or if you add one more crossing here, the readmaster move 1, where you can undo this when you do the identification, tells you that there is no one braid and one knot. There are many braids and one knot. Okay, so the map is not unique, but the non-uniqueness is very fixed, very stringently. Like that these are the 2 moves which you are allowed to do. Okay, so what do we have to do? If I want to construct an algebraic invariant for a knot, I can try to take the braid group representation and find an invariant in such a way that if I do Markov move 1 or 2, that invariant should not change. Is that right? Then you call it as a knot invariant. Okay, so all the knots, the trefoil which I drew can be drawn this way. And some places I've drawn the identification, some places I've done some kind of a capping, and so these are the ones which we draw it by identification. We call it as a closure, but sometimes you have a closure and a capping. So those are what we call it in general as a posse plait of braid. Okay, so if you do just a closure, then the arrows are just going upwards. But if you start doing all these complicated, some places as closure, some places as capping, then sometimes some arrows can become anti-parallel, parallel, and so on. Okay. But that's just a way of convenient way of drawing. Okay, so far the math, and now I'm getting back to Chern-Simons theory to see how they can be reproduced within Chern-Simons. Is that okay? First of all, it's topological. Size doesn't matter, and you need a theory which is independent of measuring the lengths and so on, and the one which measures is the metric. So you need a metric independent theory. That's one topological theory. There are many other theories where you can also make it topological by other things, but here we are looking at explicit metric independent theories. Okay, so we're going to confine to S3. S3 is very close to R3, but all the points at infinity have to be identical, right? So in that sense, S3 is, and also if you look at space of flat connections and all, it is trivial. So a lot of interesting stuff in S3. So we'll confine to S3, and we look at knots and links inside S3. Knots and links are going to be inside S3. Okay. So to start with any field theory we have to give an action. Action on any three-manifold. Now we'll confine to S3, but in principle you can write it for any three-manifold. So it is a 3 form on a three-manifold. You can explicitly write it out, and you can also use gauge groups here. The A could belong to any compact semisimple gauge group. So I've written the TAs as the generators of the group G. And this, once this action is there, you can find out expectation values of observables in the field theory. This action is metric independent clearly by construction. You can see that. And you can also show that the partition function will be gauge invariant if I choose my coupling. I'm not really put the coupling, but if I put the coupling, then it will be a gauge invariant only if K is an integer. Okay. Again, observables also has to obey that property that it should be gauge invariant and metric independent. And the class of observables which respect that are the Wilson loop operators. The extra freedom which we have in comparison to the knot theory people is that in a gauge theory, I can choose different gauge groups. And even within a gauge group, I can choose different representations. So these Wilson loops can carry some representation of a gauge group G. Okay? So this freedom is something which helped us or motivated us to go and attempt classification problem. Because there they could do only a recursion relation, and this kind of changing R, changing gauge group, those freedom they did not. Okay, so an expectation value. So this K can be the trefoil, for example, and or figure 8, and you can work out this expectation. This is just formally, right? But if I want to compare the mathematicians, I have to write the explicit polynomial. Yeah.
Sorry, maybe I'm
no problem. Yeah.
Asking ahead of time, but suppose I take some gauge group like SU3, for example.
Yes.
And look at three-star representation.
Yes.
And compute.
Yes.
Then I take octet and compute.
Yes.
You get different answers.
Correct. Yes.
Right?
Yes.
And what happens to topology is not changed by this?
Topology is still the same.
It will be the same.
Yeah.
Actually,
So if you do
independent of-
perturbation theory, there is a group factor and a topological factor. Topological, suppose the leading term is a linking number, for example. The linking number doesn't change. So the topological factor will not change. The trace of TA, TB will keep changing and they will give you some different coefficient. Ultimately, the invariant will be different, even in a perturbation theory. But you can pull out the Vasiliev invariant where there is a topological piece and a group theory piece. It's always possible.
And that's always also possible for any other gauge group, like orthogonal group, if I choose.
Yes.
ON.
Yes.
Once again, the topology will be the same.
Yes, yes.
And the other aspects.
Yes, definitely. Yeah. But to see that separation, you need to do perturbation theory. But if you just do it on a complete non-perturbative result, I cannot split it out. So I'll get the total invariant to be looking different. Okay. Yeah. So there are two ingredients which goes into this computation to see the polynomial form. And to see the polynomial form, one is this redrawing every knot as a braid or a plait of a braid. That is the one thing, which anyway I've explained it even in the knot theory. Other thing is, just like your Gauss's law, which you're all familiar when you do, del dot E on a volume integral is related to the surface integral as E dot ds, we can try and, break this anywhere. In fact, topological theory, so you can break it anywhere into two S2 boundaries, and these two S2 boundaries will be oppositely oriented. And we can look at, instead of doing a Chern-Simons functional integral on this three-dimensional manifold, of course this manifold has a boundary, you can rewrite that as a state. This is one of the ingredients from Witten's work. So using these two, we should be able to write the polynomial for representation R and different gauge groups technically. Okay. So this is what was done in my, I think 30 years ago during my young days of PhD. I wanted to do classification. That was the reason why I was into it. Okay, so this is Chern-Simons functional integral can be attributed to a state on this space, and this space is where you have this conformal field theory with a current algebra symmetry. So whenever I put a representation, the corresponding primary field on this puncture is, suppose I take SU2 group, then it will be a SU2 current algebra symmetry, and the level will be given by the coupling constant in Chern-Simons. Okay, so that level is what I call it as K. And formally, any expectation value of Wilson loop operator, because they are oppositely oriented boundaries, if it is on a dual, it's a vector, then it is a dual state vector. So formally, you can write it as in a product. But what is psi and what is phi has to be determined. And for that, you need the basic basis states. So simple cases we could infer, we didn't want to go through the skein relation. We wanted to infer that if you take simple cases like this with 4 punctures, if I glue it with itself with opposite boundary, I will get 2 knots, and those can be normalized. We put a normalization to take care of those basis states. Okay, so and here you can see that if I do any number of twisting here, I can undo it. And what we wanted to do is we wanted to take that to be that it is a trivial representation when I combine these two in this curve. Okay, so this is one way in which we kind of proposed the state. And similarly for this case, we said that the middle 1 and 2, if I combine, it should give you a singlet. Okay, so these are 2 inequivalent bases. Okay, so you can go from one basis to another by some kind of a unitary transformation. We do this many times in quantum mechanics, right? We choose one convenient basis if we have an operator which are eigenstates of that operator. If we want to go to another operator, if we know that they are not eigenstate, we have to do a unitary transformation. Okay. And the rest, other thing which you have to remember is non-trivial braiding can happen between these 2 strands. So I'm putting a B with the subscript 1 to remember it is 1 and 2, and the minus to remember the arrows. If this arrow is anti-parallel, then we put it to be. These two relative sign, relative orientation is opposite, so we put a minus sign. And similarly here, both are parallel, and if you do a braiding, we call it with a plus sign. Okay. Since there are only 2 strands, I didn't put the subscript. But if there are many strands, you have to put the subscript. Okay. So and similarly, B1 minus here also. And when we write the representations for the SU2 group, it is a pseudo group. You don't need to worry about orientation when we write the representation. But if you're doing SU3 and all, we need to keep track that it is a conjugate representation. So those are small things which we systematically keep track like any group theory problem. And these are the braiding. Okay, so these are not going to be the... So if you do the braiding here, you will get back, this is an eigenstate of this braiding operator. You will get back this with some eigenvalue. And that eigenvalue can also be written in terms of the quadratic Casimirs of the representations involved. So T will be the representation in R1 cross R2. Okay. If K was, if you have to also remember that it's a current algebra symmetry, and I'm assuming K to be very large, otherwise T will also have some restriction. Okay. And similarly for the middle strands, we will do only the B2. For the side strand, you could have done either B1 or B3. If you do B3, then it is R3 and R4. But for the middle strands, we'll do this. These two are two inequivalent bases. Okay. And this is also very clear because the trilinear relation between BI plus 1, they don't commute. So you cannot have the same basis to be the simultaneous basis for both B1 and B2 because B1 and B2 don't commute. But B1 and B3 commutes. So this will be an eigenstate of both B1 and B3. Is that clear?
I have a question about this.
Yeah.
Couldn't you undo the braiding operation on the other side? I think this, you're looking at the
yeah, so braiding is done on the plane. You don't have this extra dimension. That's why bosons and fermions, there are only 2 classes of particles in 3 dimension. You can't have anyons. On a plane, you can have any phase factor under exchange. That's why you have anyons. So all these braidings are done in 2-dimensional plane. Okay, is that clear? Okay. So these two are inequivalent bases. Formally I've written T is R1 cross R2, but you have to remember that the K level will also put in some restriction. But this T should be in the intersection of these two. Similarly, the S should be in the interface of R2 cross R3 or R1 bar cross R3 bar. Okay. And these two bases are related by a unitary transformation. Interestingly, using topological equivalence of knots, we have found the properties of this matrix to be exactly like the quantum Raka coefficients. Okay, so it's not a proof, but the quantum group people are struggling to find this Raka coefficient. But since we know indirectly this, we are exploiting this to even actually give them the information. So that way we have also been playing a role to give information for quantum group people. Okay, so the properties of this matrix, the unitary transformation, is exactly similar to the properties which we are all familiar with the quantum Wigner series. Okay, so quantum Wigner 6J comes in when you have, in your quantum mechanics, if you do addition of 2 angular momentum, you get Klebsch-Gordon coefficient. The Klebsch-Gordon is called Wigner 3J. But if you do addition of 3 angular momentum, you can do it by associativity property. You can do it in 2 ways. And that will give you the quantum Raka coefficient. Okay. Okay. So I've just given you a flavor that we need braiding eigenvalues, and we also need this transformation to go from one basis to another, because you'll always have an arbitrary braid word to work with. So all your results will depend on braiding eigenvalues, 6J symbols, and we can write invariants of knots using them. Okay, so this is something which can be done. So the mathematicians, there are actually 6 authors who wrote one paper, and PT is another set of authors. In fact, all of them came to 2009 knot theory ICTP conference, and these are the mathematicians' results. Jones polynomial they have, Homefly PT they have. Now, what is Jones as far as physicists is concerned is you put R to be fundamental representation or spin half of SU2, you get exactly the Jones polynomial. If you put fundamental of SUN, we get the Homefly PT. Okay. One variable, yeah.
So how do you get the sine relation?
Scan relation can also be got, but I'm getting a direct invariant, and yeah.
How do you know it's the Jones polynomial? I mean, how to identify?
Yeah, so results are matching with all the examples, and you can also reproduce the scan relation. Yeah. So that Witten has already shown the scan relation. But what is disadvantages about scan relation is that if you don't know the lower number of crossings invariant, you cannot find the higher one, right? If suppose I want to find the n crossing one, all possible n-1 crossing knots, if I don't know, I cannot find. But the direct method, I don't need to even worry. I just directly work it out. And of course, that table has been worked with scan relation, and we can also reproduce a scan relation for every representation. And it can be verified. Okay.
So what I'm puzzled about, so if you change the representation, won't be Jones polynomial?
It won't be Jones polynomial. Yeah. It won't be. Other way of saying is it's a 4-punctured conformal block, and I have to look at the dimensionality of the Hilbert space that will change with representations. Okay, so you will have a skein relation will not be a skein relation involving 3 objects. It will be a skein relation involving 4 objects for spin 1 and so on. So it becomes even more complicated. Yeah, if a vector space is n-dimensional, a linear combination of n+1 dimensional state has to be 0. That will give you a skein relation. And each vector state, I would write it as a braiding operator on that state, and then I'll get a skein relation. That's the way it is. Okay, so skein relation reproducing is not difficult. Yeah.
Are there examples of knots where following the Jones polynomials are the same, but colored Jones are different?
Yeah, there are. Yeah, so it's progressively improving. So if you ask spin 1, there are still knots which are not distinguished. Then we go to spin 3/2, spin, at least we don't want to go beyond SU2. Computationally, we find it more easy. But then we are forced to go to SU3 or SO and so on. So,
but higher spins are always more efficient.
Looking like, I don't have a proof, but that's the way it looks like. Yeah, it's becoming progressively better and better. That's what we see from the data. I'll give you some examples to get the flavor of it. Okay, colored Jones is the jargon which is used for other representations. Okay, so if it is not fundamental, they call it colored Jones, and similarly colored Homefly PT. I've not put one more table here. There is a Kaufman polynomial. Kaufman polynomial doesn't need an orientation. You don't need to put the arrows on the knot. So if you don't put an arrow, no crossing can be of 2 types. You can either have no crossing this way or this way. So there is a skein relation involving 4 pieces, and that corresponds to SO and Chern-Simons. Okay, so that table I have not added here, but it can be added. Even the Kaufman can be given a Chern-Simons interpretation, and then you will have a colored Kaufman for higher dimension representation. Yeah.
From the point of view of classification, getting these invariant polynomials, is it really important to choose a compact for this?
Yeah, so unfortunately here I need it to be, a compact lead group. If you take non-compact, K can be anything, and then gauge invariance and all these things have to forcibly make us have K to be a. Okay, so in some sense SL2C Chern-Simons can be done, but they have connections to gravity. But SU2, SO3, all these compact groups are ones which are connected to the topological aspects. Okay.
What about symplectic groups or the exceptional groups?
Those can also be done. Yeah. Those are also in the same class of compact semi-simple groups. Yeah.
So they give you invariants.
They also give you invariants, but there are some relations between orthogonal and symplectic with some change of variable. I can show one goes to the other. So there are ways in which I can see that. Yeah.
So I have a question. I mean, suppose you take SL2C, complex group.
Complexification can.
So all these expectation values are finite?
There the things are all going to be very different, but when you do the perturbation series there, let's take SL2C Chern-Simons. So SL2C you can do for all these manifolds, three-manifolds. Okay. Only thing is in SL2C you will have A and a conjugate A bar field, and K will be replaced by K plus sigma and K minus sigma. So you need to keep track of these things. And what we do in the perturbation theory, if you take the imaginary part of those coefficients, there are some connections to the volume of the knot complement. Knot complement means it's still a three-manifold where the knot is removed. So those have a lot of connections there. So the geometric aspects which you study in SL2C Chern-Simons, there's also connections to topological aspects which we study in compact groups which we don't understand the meaning. This is what is called Kashif's conjecture, volume conjecture, where colored zones, if you take the large color limit and do some evaluation, you get a volume. And that same volume you get if you do it on a knot complement, but in SL2C Chern-Simons. So the geometric quantities here have some connections to topological quantities, but nobody, it's still called as a conjecture. But there are works on that interface on the SL2C. Yeah. Anything else? Okay, so you'll ask, what is this variable Q? The variable Q is related to the rank of the group and also the coupling constant. And if you make this variable Q to be this, where n is 2 for SU2, and for SUN, you will have another variable A as Q to the n. So this is dependent purely on the rank, and this one is the Q variable. So you can write, these are two variable. The home fly PT are two variable in variable A and Q, and this one is in variable Q. Okay. So we can write all the polynomials provided you know the 6J symbols and the braiding eigenvalues for any braid word. Okay. So that is what has been a challenge, writing the explicit polynomial. One of the open question is that the 6J symbol for SUN, SU2, everything is known. Okay, you give me any braid word, I can work out the polynomial. But if you take SUN group, even SU3, for example, it becomes, this expression is not known. The quantum 6J symbol for arbitrary representation is not. That's why I said, we gave this input for symmetric and antisymmetric from the knot invariance approach, and that is actually a new data for people to use the 6J symbol. For SUN, symmetric and antisymmetric, we have provided the closed form expression. But from knot invariance. This is the work with Satoshi and Zodin, who was my former student, where we did a class of knots. Okay, so coming to the polynomial form, there is a certain class where the computation becomes much more simplified. Okay, I initially thought any arbitrary braid word closure can be brought to this form, but unfortunately not. So these are called the arborescent knots, where you can draw diagrams of this type for only a class of knots. This class is also a huge class, where you see that each one is like a finger, and each finger has an S2 boundary with 4 punctures. Okay, so this kind of drawing makes the computation very simplified. That's why that quasi-plat braid and all is useful. In this, all the arrows may not be going up in every finger. Some may go up, some may go down, but equal number. If 2 are going up, 2 will come down. And because the net number of crossings here should always be balanced. But you can draw a class of knots, they are called arborescent knots, and then these invariants, we could work it out for any symmetric or antisymmetric, the polynomial form. Because we know the Raka matrix, the 6J symbol. So we could work this out. This is a huge data. This is something which was useful even in the topological string duality validation. This data was very, very useful. Of course, any knot cannot be drawn because this is something which I didn't know, but later on I struggled even for an 8-crossing knot. I couldn't draw it, and then I found the mathematicians' proof that there are a class of knots which are called non-arborous. Okay, so the computation requires some building blocks. This I already told you that I use this normalization, this basis and this basis. Of course, this is for single boundary, but I can have 3 boundaries, 2 boundaries with, with the time evolution by an arbitrary braid word, can have a multi-boundary. If I give you all these states, okay, as a proposal like the way by using topological equivalence, then I can also do mix and match. You can do braids here. If I do it between these two by a horizontal braid, I can try to redraw the same thing by putting 3 boundary states, putting in the middle 2. You can play around. And for each one, I know what the state is. And I just take an inner product of them and I get the states and write the polynomial. So I've given you some examples here where I redraw it as a kind of that, at every point, it's only a 4 punctured boundary or a non-trivial braid word. And we can work out. One example I've elaborately done here. Rewriting it. In fact, this invariant which I've written is true for any compact semisimple group with arbitrary representation. In terms of your Raka matrix and the braiding eigenvalues. This is true. But to find the polynomial form, I have to tell you what this is. This anyway we know because they are quadratic decimal. Knowing this is a non-trivial issue for other groups and other representations. Even for SUN, mixed representation, we don't know. Right? And just to flash for you, SU2, a closed form was given like this. And we got almost the same form with some additional C factor. And that C, if I put it to be 1, we get back the SU2. Okay. The advantage of symmetric is it is similar to the SU2 representations. If you go beyond symmetric, there is no analogy to SU2. Right? All symmetric rank 2 can be mapped to spin 1. So there are a lot of advantage. But beyond symmetric, then you start losing things. And this anti-symmetry looks like some kind of a toggling of a transpose. So whatever happens for symmetric tensor product happens for the anti-symmetric tensor. Okay, so that's why it was useful. So now comes the classification. One is mutation. Okay. This is still an open question. So especially with all this COVID and mutation happening, everybody keeps asking me how you have a solution for mutation, but this is something which is in knot theory. Mutation is seen, at least by the knot theorists, as an identity operation. But mutation, I'll explain by diagram what it is. And chirality is another one. If you take a knot and take a mirror image of the knot, those two are not, you cannot connect it by a set of readmaster move 1, 2, and 3 for any general knots. So there is chiral knots, there is ampichiral knots. Chirality detection is also an open question. So can Chern-Simons invariant detect mutation and chirality? So chirality, this is where your information for you comes. Up to 10 crossings. We find that there are, see, when we went up to 8 crossings or something, spin 1 was better for chiral knots. But when we went to 10 crossings, 2 chiral knots, if you take chiral knots and take the mirror of the knot, if you get the same polynomial, then you know the chirality is not detected because the knot and the mirror knot, I know they are different. So we took the spin 3/2 here and we showed that spin 3/2 can distinguish 942 from its mirror image. Similarly, 1071 from mirror image. Okay. Coincidentally, I think this was done in 93 and some of the chemists were struggling with 942, proving 942 and 1071. The Princeton group were chiral. They had a paper on topological chirality, and they even referred to us and they thanked us, saying that ours actually helped them to show sufficient and necessary condition when it should be chiral in a physical chemistry paper. So in some sense, I feel a lot of interdisciplinary people are thinking about, and just to give you a flavor of what is mutation. So that was done up to 10 crossings. Okay, when we go to a 16 crossing knot, there is a knot whose mirror image is actually a mutant of it. So there's some confusion there how to detect them. I still don't have an answer to it. Okay, but this is a 11 crossing knot. What is mutation is you take this region out, do a 180-degree rotation. Okay, here I've done a 180-degree rotation about this axis. So this has gone into this. Technically, these two are, this operation should not be an identity operation, right? Because I know mathematicians have shown that this is topologically inequivalent to this because they don't have Riemann to move 1, 2, and 3 to relate them. But even within physics, if I do SU2, the polynomial for this and polynomial for this for any representation was same. It shows it's an identity operation. So we did SUN, then also it was same. And we were bothered. Is Chern-Simons bad? It cannot detect them. These are questions which really made us think. Formally, in my thesis, I gave a proof by the conformal block language that the operation, mutation operation, turns out to be an identity operator for symmetric representation. So what does it tell me is that you need to go beyond symmetric. You need to at least go to the octet diagram in SU3 and to see whether this operation can be distinguished. So this is where Zhu and Joker, purely from conformal field theory, they worked out this Wigner 6J symbol for the 2, 1, which is an octet diagram. They worked it out. Since they had the data, and we know our formal invariant for any representation, any group, we replace SU3 and put this representation data into it. And we explicitly showed that this polynomial and this polynomial were different. So Chern-Simons is really detecting or classifying the examples which the conventional Jones, Humfly, and Kaufman could not distinguish. Okay. One of the crucial point which plays an important role, which we all overlook, this we also overlooked when I was writing my thesis, is that when you take tensor product of octet with octet, okay, you can get a diagram with 3 box, 2 box, and 1 box twice. I took both of them to have the same features. But now with Zhu and Joker's, we put an additional index, you could call it as refinement, multiplicity index. And with this multiplicity index, which is also put in here, we could actually do systematically and show it is not an identity operation for mixed representations. Because I was puzzled how the identity operation will be not identity when we go. So we could show the mutation operation is not identity because of this multiplicity issue. So multiplicity plays a crucial role. And this we had done for many classes of mutants and we got distinct results. There were, of course, many more mutants which cannot be distinguished even after we use the 2-1. Okay. And we needed some more works. So what we did is we went to really 4 box in the first row and 2 box in the second row, where some irreps occurred more than twice also. So that was forced on us. A heavy computation done just for SU3. We couldn't do it for SUN like the way we did here. For SU3 we did, and we did distinguish those mutants also. Okay. So it's progressively better and better is what we, suppose somebody comes and gives us 2 data, it's not distinguished, we find a way of because we have this huge pool of different representation, different age groups. Okay. Okay, so this is also an arborescent knot, the double twist knot. So there are a lot of recent developments from
representations which can distinguish mutants.
Ah.
Cannot distinguish something else that other ones could distinguish earlier.
Yeah, something else we have not found what is something else. Otherwise, we would have. Actually, it came to an extent that we found an identity operation for any mutants. So that's why we were upset that the Chern-Simons has become closed, like we cannot use it for classification. But then this thing came up that the multiplicity helps us. But something else, whatever it is, we don't have these kind of specific operation, but explicitly working out, I feel it will distinguish.
So I think what I'm asking is something different. That imagine that you have a mutant and you have found this mixed representation be distinguished.
Yeah.
Now the symmetric representation already distinguishes some knots.
Correct. Correct.
Is it possible that some knots which are distinguished by the symmetric representation are now not distinguished by this mixed representation?
I don't think it will happen, but I can check it. I'm sure we worked out all the polynomials for mixed also. I don't think we.
The question is whether there is something which can be called the best representation, or maybe.
From the experience, I would say that as you go to a little more complex situations, it's getting progressively better and better. That's the way we see it. Like it could happen that there will be a 15 crossing or 16 crossing. As I said, one was a chiral and another one is the mirror image is a mutant knot. There, I don't know what is going to happen. So 16 crossing, I cannot say, but at least till 10 crossings, if symmetric distinguished, 2-1 also distinguished. That data we have. And this is not a proof. Huh? Chiral 942, everything, the polynomials we have worked it out, they're all different for all those knots. Yeah, yeah. Okay? Yeah. Okay, so this was the initial work with Satoshi, which we did for a twist knot. But then this twist knot belongs to a general class where there's just not one full crossing, one full twist or 2 half crossings. You can have 2s half twists. So this is the most general class. This was a recent work which with Vivek and my student Sachin, we had done this work. Where this formal invariant, of course, it's an arborescent knot, we know it. What we wanted to do is, especially we wanted to try and see, there were a lot of recent developments where the invariant should be rewritable in a general fashion. If you change P, you get the invariant for the next twist knot. It's a family invariant. Okay. Instead of working case by case, you would like to write an invariant. By changing the parameter, I get the next invariant. Or you can have a huge set of parameters and by changing it, you get the invariant. So one universal invariant we wanted to write. But this is just a single parameter. This was done and where we extracted the Wigner 6J symbol. So this invariant, if you look at this, you see that there is a piece which is not dependent and there is a not independent piece. And this is what they call it as a cyclotomic expansion. Okay. So what we wanted to do is that there were some interesting developments for every knot. There is an equivalent quiver diagram drawn. Okay. So these quivers are not new even in the ADS-CFT. When we do on Calabi-Yau threefold, you can have a quiver gauge theories. Okay, so that was one exciting thing which made me get motivated from the knot invariance. There is a way to extract what this means is not very clear, but is there a way of equivalently rewriting using the quiver information? For example, for the trefoil, the quiver is a 3-node quiver. And these are like, you can see it's a symmetric quiver. This is like a bifundamental. There is a conjugate bifundamental from node 1 to node 3. So you can write a charge matrix for this. Huh? Yeah. Is that clear? Somebody asked something.
Because for the case of braids, there were too many braids giving the same knot.
Here also you have at least one quiver, but there are many, they belong to a permutohedra. So let me not get it. At least you wanted to find one quiver for a family. Okay.
But does it go the other way also? Even a quiver represents that is always not.
Yes, that's the conjecture. The knot-quiver correspondence says that you should be able to find. I'll show you the algebraic expression and then you'll see. Okay. So this is the data for a simplest example, that is a symmetric three-node quiver. And formally, these are my home fly PT invariants or colored home fly PT invariants, where R is any arbitrary symmetric representation and you sum up over R. Okay. So this, and X is just a variable where you write the generating function, and QK to denote that it is a quiver associated for the knot K. Okay, so this invariant is for some specific knot K, and I'm going to confine to SUN, and these are summing up over symmetric representation for which I know all the results. This invariant can be rewritten. Okay, this is a very non-trivial exercise. Okay, formally, this is a conjecture that this invariant can be formally written where the Cij is your quiver charge matrix. Okay, and this has connections to the mathematician's results on Donaldson-Thomas invariant as this one. This omega dj is the Donaldson-Thomas invariant. Okay, this is true for any knot, but rewriting this in this fashion is a very non-trivial exercise. To do that, if I can rewrite this in terms of Q Pochamer or for a family of knots, then this could be done and I could extract the Cij. So this was one of the interesting things. We still don't have an insight what that quiver matrix means, but even rewriting it in this fashion is still a conjecture. And for some classes, people had done simple torus 2, 2n plus 1 torus knots or twist knots people had done. We wanted to do it for a double twist knots, which I showed in the previous diagram. And this work was recently appeared a few months ago in PRD, and this was for the double twist knot, where we actually found a quiver charge matrix for 2, s. And also we could do it case by case, but we still couldn't find a pattern for a general double twist knot. Okay, so this is something which, it's not just a simple family. We wanted to do it for a universal family, which we had done in the earlier case for the arborescent knot. But even for the simple family, it's a lot of struggle. So anybody is interested can actually take a look at it and see whether it can be generalized even for K, P, S. The P, S I showed you here in this diagram. Okay.
But the other way seems simpler in the sense that at least if you know the quiver charge matrix, you can just expand it out and get a polynomial.
You can, but then which polynomial, which knot was also another thing which is not very.
Even a polynomial, you don't know how to identify the polynomial.
The only good thing about this is that to do this, you don't even need to go to SUN. The charge matrix is independent of the rank. If you do it for SU2 also is good enough. So we actually did the SU2 because that was much more handleable because we can remove one more parameter, the variable A out of this. Okay. So small one more point is there. Can I take another 5 minutes? So the last thing, the second or third slide I said classification of 2D surfaces. Classification of 3D is also important. I just confined to knots. There's a lot of ways in which you can see the 3D from knots perspective. So that's why I want to stress here. To define different three-manifold, to distinguish different three-manifold, you can explicitly, if you can find a way of working out the partition function for different three-manifolds, then that is a good three-manifold invariant, right? This in mathematicians have called this as Reshtikin-Torayev or Witten-Reshtikin-Torayev or WRT invariants. Okay, they are actually proportional to Z of M up to a proportionality factor, but its main is the Chern-Simons partition function. But what did I do? I kept myself on M to be S3 because I said it's much easier to do S3 because R3 with all points identified, right? So with that knowledge, with knot invariants in S3, can I construct other three manifold? And that is also available. Mathematicians call that as a surgery. Surgery of frame knots and links in S3 leads to three manifolds. So this is the Licorice-Wallace theorem, and we need to quantify algebraically what it means. Diagrammatically, let me give you a picture. You take S3, you take some knot here, you thicken the knot, that's what you call it as a tubular neighborhood of the knot, remove it out. So when you remove it out, it is also having it's like a solid torus with the boundary which is T2. This is the complement of this, which is also a solid torus with the boundary which is oppositely oriented to this T2, right? What you can do is that for all the T2 boundaries, you can have a meridian and a longitude. If you just identify the meridian with meridian and longitude with longitude, you get back the same manifold. If you start identifying a longitude with a meridian and meridian with a longitude, you start getting a complicated situations. Okay. So this is the procedure where you can have a homeomorphism on the toral boundary, and then gluing will give you a new three manifold. Okay. Simple examples as S2 cross S1 can be seen because in partition function language, by canonical quantization in Chern-Simons, I can say partition function is 1. I can find what transformation I should do on this partition function to get the partition function for S2 cross S1. Okay. So this is the procedure, and we should quantify it. Or Licorice-Wallace theorem of getting partition function for other three manifolds, I should be able to rewrite in terms of frame, knots, and link invariants. Okay. Of course, it's also not unique. There is a Kirby moves which tells you that a set of knots or links on which you do surgery will give you the same three manifold, but that's also a finite set of moves. That's also known. Okay. So in 2000 and 2000, I think this was also 1999, probably I was a postdoc at HRI, and then it got published in 2000 with a postdoc who was a faculty. She was on a sabbatical in TIFR at that time. And this was done with, instead of looking at as, this is called cabling. There's a way of putting a K bunching of every knot, and she actually helped me how to work out this, and I showed that that bunching can be seen as tensor product. So there we reconciled a mathematician's result with physicist's result for SU2, and with Cowl we wrote it for other SUN also. Then we got back here in 2017 onwards. Gukov has a neat way of refining it. As I said, that the polynomial of Jones had integer coefficients, whereas this partition function does not have that kind of a behavior. Okay, so he came up with a nice way of writing the partition function as a refinement. Let me not get into details what these B's are. These are like, the space of flat connections you can take. These Z hat have an integer series. They call it as a Q series. And we wanted to extract these Z hat of B, knowing so many information about various gauge groups in our language. Okay? So what we found, this is with my student Sachin in 22, what we found is that the Z hat, this one, whether we do SO3 or SU2, it was the same for a class of three manifolds. And let me not get into what those three manifolds are. They're called negative definite Plum. And we were worried why it is the same. We wanted to see why it is same. We thought it should be the Lie algebra, but we wanted to verify this. Then we looked at SUN mod ZM kind of quotienting groups. And formally, we proved in this paper a few months ago that Z hat is dependent on Lie algebra. So this is just to give you the recent developments where we got into it with our knowledge of what we had. And let me conclude. So I've given you a flavor of so many exciting interdisciplinary, and historical information. And then I briefed you on essential features of knots, braids, how Jones polynomial is computed, computation from Chern-Simons theory, and focus on mutation and chirality, how Chern-Simons has shown improved classification. Of course, quantum Wigner 6J symbol for any representation is still an open question. Okay, so this is still, one is the multiplicity issue, which makes us harder, but it's still an open question. And recent works on quivers associated to knots and Z-hat for three manifolds, we could get in and find some interesting results. Thank you.
Yeah, hi. Thanks for the talk. In the computation for the polynomials, the Jones, color Jones, Hornfly, PT, whatever, what goes is in the is the parameterization of the knot, right? In the sense that you need a map from S1 to S3 that characterizes the knot, and then you start computing from the Wilson loop, what you showed, and identify this Q as sum e to the power 2 pi I by K plus N.
Yeah.
Now, when you talked about chirality, from the parameterization, this map that characterizes the knot, it's similar, right? The chiral
similar.
thing.
It's just that because you take a mirror image, the braiding which was looking like overcrossing would have become undercrossing.
Yeah, it will just
so the
invert.
eigenvalue will become inverse, or Q becomes Q inverse.
Yeah, but you're saying that the polynomial is not able to distinguish, which means that
the polynomial is not going to be invariant under Q going to Q inverse. In general.
Yeah.
You saw that, right? Q plus Q squared minus Q cube for trefoil. Trefoil star will be Q inverse plus Q minus 2 minus Q minus 3. Like Q will become Q inverse.
Q bar, okay.
That polynomial will not be same. But if you do it for figure 8, there is a Q plus Q inverse, Q squared plus Q minus 2. So when you do Q to Q inverse, it will remain invariant. Figure 8 is actually an antichiral knot. But 942, what happens is it has a symmetry. If you do spin half or spin 1, under Q going to Q inverse, I get the same polynomial, unfortunately. But Q3 by 2 is able to distinguish it.
Is it true that most things are achiral? Most knots are achiral? By achiral, I mean the chiral image is actually the same as the...
No, that's not true. No. Okay. At least up to 10 crossing, I know I can count the number of antichiral knots. Many knots which are chiral. Yeah. That's right.
So do you have enough Chern-Simons invariants to say that, I mean, have them different on its...
See, the thing is, for the three-manifold invariant, I can't put a representation. See, the thing is, it's like I have to sum up over all the representation. That summing up over all representation, I can do it for SU2 because I know the invariance of the knots and links for any representation. Even if I go to SU3, I need mixed representation invariant, which I don't have. If I have, then I can tackle that. So the complete set of invariants for SU3 onwards, I don't have. If I have it, then I can do the three-manifold Z of M in general. For some cases, I can do, but not for all cases, no. Where it doesn't involve Wigner 6J, I can do. But then that is not enough to even answer that question. But definitely for mutants, I can say formally it will be different. But I cannot say that because the knot invariants are different. But that is not a proof. I have to give what is Z of M. Formally, I can say what is Z of M. Yeah.
Any other questions? I have a broad question.
Yeah.
It's kind of, it's not clear very much. But what do you look for in an invariant? What do you look like if you guess that some polynomial may be classifying all knots or something, what property do you think? I mean, the way they do it is they find something which doesn't distinguish.
Yeah.
But would you say one feature they look for so that you kind of, you know what I mean?
So suppose I look at a polynomial, I can see whether it is having the skew to Q inverse symmetry.
Yeah.
If I look at that, if I see Q to Q inverse symmetry in the polynomial, I will perhaps it is antichiral. That's what I would say. But the mathematics literature explicitly gives which are chiral, which are non-chiral from topology point of view.
Yeah.
So if it is not, it is Q to Q inverse is happening, but it's a chiral knot, then I know I have to go to some other method of distinguishing it. That's the way we go through this. We know what the symmetry will mean here. We know when mutation happens, what should be the modification in the polynomial, we know.
I see.
But whether the modification
is enough to distinguish, that is not clear.
Yeah, that's not clear. It can be an accident, right? Like so that is what happens.
But what else do they look for? Q goes to Q inverse is one
Q
thing.
goes to Q inverse for chiral knots. For mutation, it's something non-trivial operation.
Okay, some symmetry which is
No,
non-trivial.
we need to put in between a matrix which takes you from one state to another. See, I write it as an inner product. I have to insert some non-trivial matrix there.
Oh, okay.
So after
to
you
see
put the
that it's invariant, is it?
Yeah. No, if it is invariant, then the mutation is not detected.
Oh, I see what you mean.
If I do this and I get a new state and get the inner product also giving me a new invariant, then I know mutation is detected.
I see. So it's very, very complicated. That's all I can say. Thank you so much.
I mean, do you think that there will be a polynomial which will distinguish all knots, or you have to keep going up higher and higher representation as you go to more and more complicated?
I don't know whether proving is easy, but disproving may be easier. So I don't know if we
can one hope to disprove it? That maybe you have to keep going.
That's what I thought during my PhD, Chern-Simons' first chapter, because the formal proof when I wrote, I missed the multiplicity factor. But mathematicians have done by some heavy-duty computation, even for spin SU3, some specific representation I didn't understand because their computation details were not there. They said they had given it to a computer, they got an answer. But this multiplicity picture, I got that information when I went for this conference. And then it all fell in place that it is not an identity operation. So it's giving me a hope that I will, because there's a huge zoo of invariants, if one doesn't distinguish some other representation, some other gauge group should do it, but that's not a proof. We need a proof. How to prove it, I don't know.
Even then, do you expect that you have to keep going to higher representation? Can we stop in one representation that will cover everything?
Okay, so let me tell you in the mutant case, when we went to the other class of mutants, we realized that this has only multiplicity 2, that representation. So that multiplicity 2, when I did that mutation operation, it's like, order 2 groups. So it was doing like an identity operation. So we realized if you have a multiplicity 3, it is like order 3, then those states, the mutation operation will be in. So there we showed this. But if there is something where I find that the order 3 is not enough, I need order 4, then guess. Instead of 4, 2, I have to go to some other. But beyond that, I don't know how to guess. Yeah. But it works. 4, 2 worked actually. Numerically, we did. There we couldn't do for any arbitrary n. We could do only for SU3. That itself was a high rank matrix to work it out. So I think at some point AI will take over. I hope so. I don't know. Vishnu Janjala is like at it. He says he can do many things. I will see. Yeah.
Regarding the fact that these coefficients are integer.
Yeah.
You earlier said that this was a surprising puzzle. But what is the current status like?
Yeah.
Even these mixed representations all give you
integer
coefficients, some positive, some negative. But
yes. So positive, negative, we have understood. We do something like a cobordism. By what cobordism is, take these two boundaries to be three-manifold. Okay. And then the evolution, take this one more thing. So it becomes like a cylinder, which is 2 dimensions. So now 3 and 1 will become 4 dimensions. So in the 4-dimensional language, they introduce one more parameter t. Okay, and Kohanov invariant involves that T parameter. Maybe I should write it on the board. You think I can write here?
Just left of the screen.
Ah. So Jones polynomial was in variable Q. Okay. So Kohanov polynomial becomes in variable Q and T. And if you take T to minus 1, so let me write the okay, so this is one way of writing where these coefficients are all positive integers. Okay. And if you take T to minus 1, then you get the Jones polynomial. Okay. So some T's will be minus 1, then this integers can become negative. So we understand this. And this Kohanov has shown that it is a bigraded homological chain where this gives you the dimensionality of that homological chain. So it has to be positive integers. So this is known.
But it's not quite a counting. Is it counting something?
Huh? It's a dimension of the Hilbert space of a bigraded.
Each coefficient is a.
It's a dimension of some Hilbert space. Okay. So there's positivity. If you ask a physicist, yeah.
Is it an infinite series or it is also a polynomial?
It's also a polynomial. It goes from cutoff is fixed. It's not infinite. Okay, so it will be from 1 to some number. Okay, let me know. I don't know the number. That number is some number, but it's finite. It's a finite thing. And physicists, what they say is Oguri-Wafa, topological strings conjecture. These can be accounted as number of M2 intersecting M5 branes in theory. Okay. So there is a way of understanding these integers, at least for fundamental representation. For a mixed for a higher dimension representation, it becomes some reformulated invariants, and then they conjecture for higher representations and reformulated invariants, and those they couldn't check other than unknot, and these we could check. But there is a lot of things, richness, where you see the integers can be given a meaning to it. Even if it is negative, from this picture of cobordism, you can start seeing that.
There's an analog for this complex.
Everything, yeah. That's called Kono-Rosansky invariant. But that is done for fundamental. And then there is colored Kofanov, colored Kono-Rosansky. A lot of things mathematicians have been doing. Physicists also does it, but then there's something called as a reformulated invariance. There is integrality conjectures, which is predicted, Gopakumar-Wafa, integers, which are related to Gromov-Witten invariance. Those things have also been done. So which parallelly physicists can also do with this data. Okay. Yeah.
Thank you so much, Rama.
Thank you. Thank you.